So perhaps you have of course seen the announcement of the talk. So and this particular one is a thing which has to get interest of people or students. I wrote about this one T20 match against Sri Lanka, and everybody who is watching the game would be, they may have their own take as to if you have 3 wickets remaining, 2 overs and 20 runs to score. Different people, somebody will say maybe almost sure India is going to win. Somebody will say maybe 90%. Somebody will say no, only 70%, and so on and so forth. So perceptions will differ. Now the question is, can we build a mathematical theory and make a prediction about the fate of the match? Okay. Other interesting things. Suppose in this scenario, first ball is made and Kohli hits it huge, but it is not a six. It is stopped just short of the boundary and is fielded quickly, and it's only a single run. Now Kohli is no longer at the receiving end. He's the runner. He's not the facing the next ball. Then all the probability assessments calculations will change, right? You all have, those of you who are into cricket, who lovers of cricket, would have gone through all this. But these are not very specific about cricket. Such questions are interesting in whatever game you may like, football or tennis, any of these games. There are these questions because typically viewers want, they are viewing something only if they support one of the two sides, and they want that side to win and the other side to lose, and constantly their heart rate goes up and down. It's depending on whether their side they're supporting is ahead or behind. Okay? So constantly everybody's mind is doing this, and question is, can we do it through a mathematical model? Okay? That is the question. So now, in the introduction, another thing was mentioned about CBI. So briefly, here is a very interesting question, especially since you are students, and I suppose by now all of you would have appeared for some exams which has this multiple choice exams, multiple choice questions, right? Now, so this is not a hypothetical question. This is something which CBI had consulted me. A CBI officer had walked into my office in ISI Delhi and asked me this such a question. So 30 students in a multiple choice exam. That exam had 3 sections: maths, physics and chemistry, and 30 of the students had identical scores: 53 out of 60, 49 out of 60 and 46 out of 60. Let me mention that this was an engineering admission test, and this is not 20 but maybe 18 years ago. Okay, and not IIT JEE, but some prominent thing in Delhi. Okay, and this had raised it became news that suspicion of scam, and I read in the news this, and I looked at it, and what do you think? Does it sound fishy? Unlikely to happen? It does. Can we conclude that the students have cheated? How they have cheated is a different question.
Yes,
Whether
sir.
you think you can conclude, okay? Now,
Sir, I'm pretty sure because I did some rough calculations. The chances happening is around 1 in 2E155. In other words, it's impossible.
okay. Now, suppose, let's say, how many of you are right now here? You are 62. So, if we discount us, so there are at least 55 students now. Okay. Now, suppose I give you a class 2 level math test, class 2 level mathematics test. Okay. Some very simple math question as an MCQ. And let's assume you don't cheat. Okay. Quite a few are going to get identical scores.
Yes, sir.
Right. So what does it tell us? That getting identical score doesn't necessarily tell you that you have cheated. Right? So the problem.
Everyone getting identical scores in one section isn't fishy. Everyone getting identical scores in three separate sections is fishy.
Okay, so I will agree to that. The three sections matching is more fishy. Okay, but suppose I create three sections of one class one, one class two, and one class three. Okay, so what this is, these are telling you two things. One, also the answers will be different if there are only, instead of your 55 students here, suppose it is written in a CBSE exam, and by mistake they put in a very easy question paper. What was meant for a class 3 paper went as a higher secondary paper. Then there are going to be huge number of matches. Out of 1 lakh students who wrote, maybe 70,000 may get identical score in the math course. Right? Maybe 10,000, but 10,000 already is huge. So it is telling us various things, that just what you see on the screen is data. It raises marks, it is fishy, it raises questions, but you can't really conclude much unless you got little more into the problem of what was the question paper, how many total students, number of students, right? 30 matches, but how many wrote? Is it 30 out of 100? Is it 30 out of 1 lakh? It is 30 out of 10 lakhs. All these things need to be answered. Okay. So, I told the CBI inspector who had come to see me.
Oh, right. I understand. Because if there are enough students, then the pigeonhole principle guarantees this should happen if there are enough students.
Yeah.
Then pigeonhole principle said this should 100% happen.
Yeah.
The chance to E155 is only if there are 30 students and all 30 get the same scores. But if there are 1 million and all 30 get the same scores, not fishy at all.
Yes.
Correct.
So
if I can just interrupt Professor Karandikar, there is one question in the chat that came in that did everyone get the same questions wrong?
Now, so very good question whoever asked me, because this is exactly what I told the CBI inspector. I said that, look, this is the thing that you have shared on the newspaper. I said I can conclusively give you answer if you share with me database which you have. Let's say at that time there were maybe about 50,000 students writing. This number may be wrong, but anyway. So I said each 50,000 student, obviously you have put the data in some database, say Excel sheet or something, and there were 180 questions. So for each row for each candidate and one column for each question, if you share with me the answers. He said, yeah, sir, we have coded the answer as A, B, C, D. For A, B, C, D is correct, and omission means O. So A, B, C, D, O thing, that this is a standard thing used in various frameworks. So I said, if you share with me the entire database, I can conclusively tell you, because just maths matching is not the same thing, right? So he said, sir, sorry, we can't share that with you. It's secret information. I said, sorry, then I say it's fishy, but there's no, I can't write down a testimony saying that this shows that there is a, cheating. Okay. So,
sir, I did the maths. So basically, this is guaranteed to happen once if 5.2 billion people take this test.
Yeah, but you are not looking, see, at this moment we are looking for, does it tell you that there is that there was a fraud? Okay. So how many out of that, etc., etc. So just hear me out now. So I told them that they said we cannot, and I said that then this is fishy, but not enough for me to say that yes, there is a fraud. Okay. Now, the next day the officer again comes back. He says he has checked, and they cannot share the entire database, but they can share with me the data related to these 30 questions, students. So their answers on each question they can share with me. So now I can see that how many matches, how many correct answers they are, any two are matching and so on. This is giving me only total scores. And as soon as I opened that database on my laptop, or at that time I was not using laptop, it was on my desktop, immediately what I saw, that not only totals are matching, their answers on each of the 180 questions were matching, including the ones they had omitted, the ones they are right, and the ones they are wrong. Okay? So after that, I was convinced that there is cheating and it is a matter of having to write a report. But this example will tell you that sometimes people jump to conclusions by just looking at some data. And these days, last 2 decades now, this word data science and data and all that is buzzword everywhere. As soon as you see some data, you quickly want to jump to a conclusion. And this is a warning that try to find out whatever you can about how the data has been generated, from where it is, etc., etc. And then you can make fairly valid conclusions. Okay? So, you saw the importance. Now, suppose I have given a very easy question paper also, then correct answers matching doesn't tell me something, but the wrong answer matching still tells me something.
Sir, it must have been someone cheating.
Absolutely.
Sir, but if you tell like more than 5 lakh students are writing the exam, there's a chance they might not be sitting near to each other. They might be sitting here. According to the probability, I ran some maths and it's obvious to happen if the total number of students who are writing are 64,080,000. But it can also happen if there are only 30 students are writing. But because everything has some probability, right?
Yeah. So to make a conclusion, see, this is like a court of law. I am writing a report. Okay. So just that it can happen will not mean that therefore it is not cheating. Likewise, it is unlikely to happen doesn't mean it is cheating either. So I have to make, it's like, okay, you all have heard about fingerprints matching, right? In courts. So if there is a crime and then there is let's go back a few hundred years ago. So if there is a crime, it's a murder is there, you would have seen in movies and all that, maybe in court case. So there is murder, then they'll try to find who are the suspects, and early on they'll just be on who says what. Then somebody came up with this about blood groups. You all know blood groups, ABO. Okay. So at the murder scene there is blood. They see what group it is, and if one of the suspects, the group is not matching, he can be let off. That no, he is not the murderer. That evidence is wrong. On the other hand, if the blood group matches, then again, depending on which group it is, you can come out with what are the chances that the blood group will match. So then there is a suspicion but no proof. But if the blood group doesn't match, they can be let off. Okay?
Sir, I have a doubt.
Yeah.
Sir, but there are many people like in one place, and most of them have the same kind of blood group. And how will we find the culprit, sir?
Okay. So this is, I'm just starting point. This is more printing. So if people who cannot read and write and cannot sign, they have to put their thumb impression, as they call it. Okay. So everybody's thumb, there is an impression, and that is a fingerprint. Okay. And then there are experts who can match whether the fingerprints are the same or not. Now already, if you draw 2 times same, within a minute you put 2 fingerprints, you can say that they are same, but will they match exactly if you try to store them as some database file or some encode them and then match? It may not. So they are approximately same but not exact. So then all kinds of thing was developed, and based on that, yeah, somebody wants to ask.
Arya?
Okay, that's okay. So now the fingerprinting thing was developed, and there are fingerprints experts who can match and say that yeah, these fingerprints are matching. So blood group was a beginning, but then came fingerprinting, and then that raises more questions. And as time is passing, now we have a DNA of an individual, and they can take a DNA. They can take a sample of the hair, and from there they can figure out a DNA. So as time and science is progressing, all this is becoming increasingly better, but still it is not perfect. All it can say is that it is likely or unlikely. How likely, how unlikely. Okay. So this starting point I did because whether you study probability or not, you will see its usage all around you, be it games, be it legal matters, be it whatever. Okay. So now one of the things is that in most books, that as yet you probably have not had a book on probability, but if you see a book on probability, almost all the beginning things are about tossing a coin or tossing a dice. So students have asked me that why should we be interested in these events since they are taught at the same time not to gamble. So this is, sir, why do you, one teacher comes and says, no, you should not, moral science or ethics or whatever, that we should not gamble. And then the probability teacher or maths teacher comes and teaches us probability and takes this example of coin toss, and isn't this contradiction? So for a minute, let's keep aside, okay, why we bring in these questions, coin toss and so on. But we saw by our discussion already that these questions are important, probabilities of events, and does something look likely or unlikely? And somebody can say, I'm not interested in cricket, why should I worry? But well, in legal matters also it counts. You do write exams, and suppose you are suddenly challenged because saying that your score is matching with so and so, so you must have cheated, right? So you have to be worried. The probabilities and such things can come up anywhere, and therefore the better that people understand, so that at least they use it correctly, not incorrectly. Okay. Okay. So we'll take a few examples. Okay. So for centuries, mankind has been dealing with when should a farmer start sowing seeds for rice cultivation? What is the right time? And even you go a few decades, centuries ago also these questions were there, and slowly they figured out solar and lunar cycles, they figured out their connection with weather and the impact it has on the rainy season, and all that helped them in developing what they can, suggesting as to when should the farmers sow. Okay. All this led to a whole lot of mathematical ideas, but I don't go on it today, but whole lot of mathematics developed around these questions, okay, starting with trigonometry and so on and so forth. However, whatever analysis people have done and experts, the outcome, the amount of rice that will be obtained after the farming in a given space, given area, is still uncertain. Nobody can be perfect. It's after all only a prediction and not a thing that you can tell exactly what will happen. But on the other hand, going with these probabilities and doing it when to do it is much better than doing it totally randomly. So I said randomly, and while I have written arbitrarily, and that is with a purpose, that most people think about random and arbitrary as synonyms. You know what is a synonym? Two words which have exactly the same meaning are called synonyms. Okay. So many people think that random and arbitrary are synonyms, whereas in my way they are not. Random is a technical term and arbitrary is just arbitrary. Somehow somebody has chosen it, no rhyme or reason. Whereas if you say choose randomly, doesn't mean choose something with no rhyme or reason, but go through the analysis and then choose it correctly. And why do I say that these two are synonyms in most people's mind? with our computer systems, laptops, or on phone, when they give the specs, you would have so many GB hard disk, so many GB RAM, 4 GB RAM, 8 GB RAM. So what does RAM stand for? Any of you knows what RAM stands for?
Random access memory.
So random access memory.
Correct.
Random access.
Correct. Now, what does random access memory do? That the inside processor, it seeks a thing, that what is the data, or 1 or 0, what is it? It is stored at such and such location on the memory. Okay. So the person here is the system. System is asking, give me 1 or 0 from this location. It doesn't tell that you pick one location at random and then tell whether it is 1 or 0. That will be useless. Right? However, whoever designed the system and gave it a name, he thought that these two are synonyms, and now that has stuck. So it is still called random access memory, RAM, whereas it should have been called arbitrary access memory, AAM. Okay? All right. So that's why I am try to be more careful when I use these phrases. And so here what I meant is, using this analysis, and if a farmer follows whatever is the prediction based on this, he'll be much better off than somebody else who says, all this is nonsense, I don't believe in it, I will just do when I feel like. Okay, so that is arbitrary. All right. So in the game of cricket, no one can tell before a match starts as to the number of runs that the players under consideration for the team will score if selected. The same goes for IPL team selection. You can make your best guess. Based on everything you know, you can try to make a choice. The selectors can't say that since we don't know for sure, we will not select a team, then no game will start. So uncertainty doesn't mean you should not decide. Uncertainty, you make a decision based on whatever you know, you factor in everything you know, try to create a mathematical model, you can call it probability model, statistics model, whatever model, and based on that, do the best you can. Okay. Likewise in medicine, when a new medicine is developed, the scientific team may be confident that a particular chemical combination is likely to work for the thing they want to address, but no one can say this with a guarantee. Moreover, there can be side effects, and nobody can say that this will not have a side effect. Indeed, for this reason, once there is strong belief, the medicine is subjected to what is called clinical trials, and based on the outcome, a decision is made to approve or reject a medicine. And especially current times, we all have gone through are still not completely out of it, the COVID and its aftermath and before math and everything, and the importance of the vaccine and how the vaccines had to be approved and used and so on. These decisions had to be made. Nobody was sure that a vaccine is going to work and it doesn't have a side effect, and yet we had to go ahead. And so all this, so that whether a vaccine or a medicine will work or not is an uncertain event, and yet based on mathematical and statistical model, one has to make a decision and move on. So therefore we need to create a mathematical model. Now you may say that, sir, how can, if the outcome is uncertain, how can we create a mathematical model? Mathematics is all about perfection, precision, and we are talking of uncertain. What has mathematics got to do with the uncertainty? Well, we have learned from history that events that seem to be uncertain in micro level, when viewed correctly, do lead to patterns at macroscopic level. Okay. So micro level means individual. So let's say the vaccine, let's say the one which was most used in India, Covishield. Okay. They developed it somewhere with some they generated data. I don't know, I have not looked at the data how many, but they generated that many, and then they were convinced that okay, most of the cases it is stopping the COVID, and it is not doing any other side effects or very little side effects. It was approved. The sample, the data size that they generated this based on may have been just a few lakhs, less than a lakh maybe. Whereas in India alone, it has been administered over, I think Covishield itself would have been administered to over 30 crore individuals, certainly more. So initially what they could see was individual pattern on the whoever had been their volunteers or whom they've chosen, and what happened to them they could monitor, and that is a micro level. There was uncertainty, there was nothing perfect. But based on that, a judgment is made. Macro level means across India, you see how many people may have had difficulties due to Covishield. Very few. It did not happen that, half the people who got Covishield got into serious issues. It did happen. Actually, it happened with me. But that is rare event. So broadly, it was covered. And so this is what I mean by what seems uncertain at micro level, when viewed together, you see a pattern. And this has been seen by mankind. Examples where extensive data has been and had been recorded for decades, centuries, monthly maximum temperature in the city. So every month the thing may vary, but depending on the name of the month, which has been based on the seasons or whatever, you can predict that Chennai maximum will be always higher than the maximum in Bangalore. Maybe 11 months at least it will be true. Things like that. Likewise, monthly rainfall in a city. So you see in newspapers that this year there was a rare high rainfall, and so on. So these data for various reasons is actually maintained for cities, and it is there for decades, centuries, high tide level in a coastal city. In India, it doesn't make that much difference, but in countries, let's say Netherlands, the Netherlands or Holland as a country, the huge chunk of the country is actually below sea level. Okay? If you measure by some method what is called the mean sea level, height from mean sea level, in India we are all above. As you go up the mountain, you are going up and up. If you travel in a train next time, when you go to a station, at both ends there are these plaquettes which show the station name. Below that there is a number, mean height from the sea level. So you can see that the heights in India are large. So, but if height is low, what it means that is, if for some reason there is rain, high tide and water comes in, it is never going to go off. In Mumbai, high tide, or in Chennai, the tsunami, there was huge high tide, water did recede a lot, but quickly it receded. It created a havoc, but it was not a permanent havoc. So, monitoring high tide levels is extremely important in coastal cities, especially if the large chunks of the area are below sea level or very close to sea level. And this, in Holland, for example, this high tide levels have been there for ages. Another one, proportion of newborn children in a city, what proportion of them are girls? Okay. So today there are, let's go back at least 100 years, so that knowing whether the yet to be born child is a boy or a girl is not known, and let's just ignore all that what has happened in the last 100 years. Going back 100 years, this was as much an uncertain event as toss of a coin, whether the next born is going to be boy or a girl. So uncertainty at a micro level, and yet people had already observed that if you look at one hospital monthly data, large enough hospital monthly data, or one city monthly data, or one town daily data, one state monthly daily data, there are patterns. They may not be exactly half, but pretty close, and the patterns stay. So what I said, uncertainty micro level, but the pattern at macro level is there, and the whole thing was that if we can come up with a model that explains the observed data That is a good starting point, and that will be a good thing to start making models for predictions. And this is what is probability and statistics all about. So let me start with the simplest case. So you may say, sir, you talked about no gambling, but now you are also talking with gambling, tossing of a coin. Now the reason is that all other things like vaccine, COVID vaccine. So then the questions, really for doing a proper analysis, you need to know a whole lot of things, and some of them are going to remain unknown. That is, who are exactly the patients who are chosen to administer the initial round, which country, which city, what is their race, are they similar to India, different from India, what was the weather there, is the weather there, not there. There will be hundreds of imponderables, and you will need to do a best of it. And drawing any analysis for any real thing can be very complicated, even in cricket. Whereas if we say coin toss, then for a coin toss, we can start talking about specifics. Okay, because whether you know the outcome or not know the outcome, etc., whether you have picked up a coin which is a true coin and you have not doctored it, you have not done some funny things with the coin, it's not a funny coin. So all of you are too young. There used to be a film which was maybe at around 50-year-old called Sholay, which is talked about a lot, and in that there are two friends, and lots of the thing, the two of them always decide who will decide what to do by a toss of a coin. And it was always the person who was himself tossing, and he is the one he's always choosing, and he was winning all along. And eventually in the film it is revealed that it was a doctored coin, both sides were heads, and therefore no wonder he knows what is going to happen. Anyway, so the phrase the Sholay coin was there, or a doctored coin. So suppose it's not a doctored coin, then you are going to toss a coin, and let's say what would you say? Is it head or tail? Somebody may say, I'm not interested. Now suppose I was actually teaching you all a course, not online but in class, and I tell that I'm going to toss a coin and each one can predict, there's a guess, is it head or tail, and there is an assignment due tomorrow, but those who guess correctly will get one extra day. Those who guess wrong get no penalty. Then obviously everybody would like to guess because there is no loss and possible gain. So
but what if that coin is a doctored coin?
We'll come to that. Suppose I convince you that it is not a doctored coin. So let me stop my share, and actually you can see my coin maybe. Okay, so I bring out a coin and in the class and show you that it is all doctored, or better still, I tell one of you to hand me a coin and I am going to toss you that. So then you can trust that your fellow students have not played tricks on you, right? So we can do that. And now, so naturally, if you have only one extra day to submit assignment, you may get, if you guess it correctly, you are all going to guess, isn't it? Is there anyone who would say, no, sir, I will not guess? I doubt. So, now what goes on in your mind?
Will it come heads or tails?
Yes. So will you say head or tail?
Tail.
Heads.
Heads.
Both. Both.
Because I will only allow you one guess.
50-50.
Tails.
Okay, heads.
Tails.
Okay, guys, hold on.
So 50-50 is all your model. You have no reason to believe one of the two outcomes. Okay. You have no reason to believe one of the two outcomes. So 50% is your model. Okay. And now I will, some of you may say head, some of you may say tail. Maybe more have said head based on a quick count of what I heard. But there were some who said tail. All right. Now, we already talked about whether it's a doctored coin or not. I said, okay, one of you hand me over your coin. Suppose there are only 50 of you and we have enough time to waste. I can say, okay, each one you give me a coin, I'm going to toss the coin you give me. And now you guess. So unless one of you is carrying a doctored coin, you know that both are heads or both are tails. If you give me you pick out a coin and give me, then your model is 50-50 still. Because you have nothing to choose which one to pick. So that is what is...
Uncle, nowadays nobody are trying to make doctored coins.
Sorry, nobody is what?
Nobody is trying to make doctored coins because it's so hard.
Yeah, nobody is trying to make, but that doesn't mean that I cannot come with a doctored coin, right? Now let us take this discussion even one step higher. Suppose here is my coin. I actually have tossed it on my table. If it was in a class, I would do it in the class. I'll toss a coin. It is on a table. Now I'm not going to touch the coin, but none of you can see what is come up. And then we go through the same question. You can guess.
Can you please repeat?
It's probability, right, sir? Like
Tails.
what? It has a. It
No.
has a. It
has a probability of
Guys. Sorry.
Correctly.
Let's take turns. Yes.
Let me say exactly my question. I said that I will toss a coin. I can see what is it, head or tail. None of you can see is it head or tail. And I promise you that I will not touch it again. Okay. Then again I ask you to make a guess. Will your answer be any different from what you gave me earlier?
No.
No, sir.
sir,
Sir, it could be.
No, sir.
No, sir.
Because you have not given information. Okay. So in this process, what we have done is we have moved away from this discussion whether or not God really tosses a coin to say which way the coin is going, which way the electron is going to move. This was supposed to be a statement by Einstein, ill-quoted various places. God doesn't toss a dice to decide which way the electron is going to spin. This is a statement by Einstein. But it is taken out of context. But even if it is true, we have taken it all out of whether there is true random event or not. Right now, if the coin is already tossed but you cannot see it, it is uncertainty your mind is because your inability to see. It is still uncertain. So let me share my screen. So I have coined a phrase which I said that so if basically randomness, if the outcome is uncertain, we'll say the outcome is random, and a model that we create for it, that is what is called a probability of the event. And I thought I had written it somewhere, but randomness is in the eye of the observer or mind of the observer. Whether or not there is true randomness, we can ignore, but as long as you cannot see whether the coin which has already been tossed, is it head or tail, it is still random as far as you are concerned. You have no information. It is still equal likely outcomes as far as your model is concerned. Now, we can move one more step. Instead of me tossing a coin, I just take a coin and place it in the class.
So then the probability will still be same because we can't see the coin, right? So if we don't even know, and you have told us that it's not a doctored coin, so that means that it could either be heads or tail. We don't know because we cannot see the coin.
Yeah. Now let's change it in one more round. Last round I change the question. Okay. This time I don't toss the coin in the class. I look at the coin. I tell them that one of the two is my favorite, and I am putting that up. And I put it on the table so that I am not going to change my mind later.
So then,
Yeah.
so then the
Guys,
only...
sorry, 1 second. Can I just interrupt? So if you have a question, I would suggest you keep your hand raised or you type that into the chat to me, and then I'll take questions so that it doesn't interrupt Professor Karandikar's flow. If that is okay with everybody. Yeah. Professor Karandikar, over to you.
So now the point is, it is no longer a random event. It is my mind. You cannot read my mind. So as far as you are concerned, okay, whether it was a doctored coin, whether it is to be tossed, now it has been tossed, or whether I didn't toss it at all, I put up something on the table. All you know is it is going to be head or tail. And you have no other information, and it is still uncertain event for you. Okay. So randomness makes therefore flow in this indirectly, that randomness is because your inability to observe all that is necessary to determine whether it is head or tail. Okay. And this phenomena occurs all around. In a cricket match, as the bowler is running in his run up to bowl, the batsman, he is constantly observing the bowler and trying to make he has a model that this guy, he puts in a lot of googlies, he puts in a lot of good length balls, he puts in a lot of Yorkers, whatever be his model, and he's trying to match his model with what he sees on the run up. And is the event random? No, the bowler has decided what ball he is going to bowl. He may make it correctly or he may make a mistake, but he has decided what he wants. But as far as the batsman is concerned, it is still uncertain, and he's trying to make guess. Okay, and he observes all the things he or she can, and based on that makes a judgment. So this cat and mouse game about me putting up a coin or me tossing a coin and you guessing to get an extra day, that is just a simplest way to describe what actually happens. Even when you are playing a game, when you are preparing for an exam, you are trying to guess what is the favorite topic of the teacher on which the teacher is likely to put a question in the exam, right? You play those games too. So as I said once again, that it is easiest to agree on the basic terms and thereby develop tools for analysis if we talk about coin toss, or if we talk about tossing a die. Okay, but if we talk about any real event, then lots of other things come into the picture. What else do you know about that phenomenon? All right. So
Professor
then,
Karandikar, we have about 20 minutes more if we want to take questions after that. Just wanted to give you a heads up.
Okay, so that is what the thing is, that if based on the knowledge and information, there is no reason to prefer one outcome of the random event over the other. We call these things to be equally likely and assign each one a number 1 by m and call it probability of an event. And remember, with this approach, probability of event is not a God-given truth that we are all trying to guess, just as a gravitational constant. So but this is based on the information and understanding of the observer. Okay. All right. So this is the phrase I talked about already, that randomness is in the eye of the observer. Okay. Without this, there were all kinds of issues when initially people started saying when this equally likely and 1 by m etc. was taken as definition of probability, then what is equally likely if their probabilities are equal? And then this is what is called a circular definition, because you are defining equally likely in terms of probabilities and probabilities in terms of equally likely. So now we have moved away. We are saying this is our model, that it is equally likely. And then we assign these probabilities. So there is a subtle difference. Okay. So how does one associate probability of events if they are not equally likely? Will it rain tomorrow in whichever city you are? Yes and no, two possibilities. Are they both equally likely? Rarely would be an event that it will be equally likely. You will have various pointers, the year of the month, the month of the year, the weather yesterday, today, temperatures, if it is late night time, how the thing has evolved today. So if we have historical data, it can be used as a pointer to come up with a probability model. Okay. So along with the data, an analyst can improve his or her understanding of the phenomena in the context of the experiment in the question. So you have data and you have understanding of the phenomena, and the two together can give you a model. So we talked about this thing already. Okay. So this scenario of a first ball in the 19th over is hit hard by Kohli, but well fielded, and only 1 run is scored. The probability of India victory will go down in most models. So earlier, when 20 balls, both the overs were remaining, it would have been something that could be different. The different models may have different answers, but as soon as you now take this in, your probability will go down. So therefore, probability is all subjective. It is all evolving. Probability of event will depend on what all information you have. If no historical data is available, then for example, COVID vaccine, we need to generate data, and a whole lot of things is around that. So loosely speaking, probability and statistics are twin cousins or twins. One part, probability says that, okay, if you give me the model, what all conclusions you can draw from that validly. And statistics is about how do you generate these probability models, and finally, how do you use these mathematical ideas that are there as conclusions in probability for actual decision making. Okay? So the two work together. So in some models, the data is public, like agriculture. In some, for example, investor or a mutual fund decision maker, what company shares they should invest in, there will be public data. There may be additional knowledge about the domains from where these various companies are there, and all that can be factored in to improve the model. So all these are very complex exercises, and the learning in probability and statistics courses is to learn more and more about such things, how to do. Okay. How much data should be generated? This is always a big question. Like vaccine, before approval of a vaccine, how much data? Of course, the more trials they do, the better off they will be. But unless they decide, you can't actually use that vaccine for a large population. So you have to balance the two. How do you do that balance? This is a very important question, and there are lots of controversies which can be related to such questions. Not just vaccine, but any other statistical decision. Okay, and these days, as I said earlier already, that there is a lot of buzz around data science and big data. Okay, so this has been buzzwords, and many people think that, oh, now there is big data available. Why do we need statistics, and why do we need probability model? You give me large chunk of data and I will get all my answers. Okay. So this is a belief that if you have large chunk of data, then put it in some statistics software or data engine as they call it, and you will get the answer. And so this is what they say, that once you have large amount of data, who needs statistics, statisticians? We can get answers from AI ML statistics engine, which is like a software package. So I'm going to give a very concrete example of what I call perils of pure data-driven inference, or decision-making purely data-driven. Namely, ignoring statistics ideas can include incorrect conclusions. So here is the actual case. I am not giving you a hypothetical case, because you say, sorry, you said it, what you said may not even happen. So here is the actual case going back nearly 50 years. You all would have heard perhaps of this University of California at Berkeley, or Berkeley University, one of the premier institutions, educational institutions across globe for decades, century. Okay. So they are believed to be, it's a public institution, government funded, etc., state owned, and it is supposedly very good in various things, doing it right. Okay. And they were accused that they were gender biased, that they are biased against women. And what was the basis? So there is graduate school. So graduate school is like people admitted for a PhD program. So somebody collected data, actual data of graduate admissions, how many applied and how many were selected. And this is the actual data, which was the basis of not quite a court case, but allegation, maybe in media. Amongst 8442 male applicants, 44 were admitted. Amongst 4321 female applicants, only 35 were admitted. So they computed some probabilities and said that this is unlikely to happen if you did this, that. It is not. If there were no gender bias, this is unlikely to happen. So there is gender bias. This was an allegation. Okay. Now you can read about it and just doing a Wikipedia thing about Simpson's paradox, University of Berkeley. If you do that, you will get a Wikipedia link, and you can read all about it. Okay. So this is what can be called pure data driven. Now, instead of 8442, that can be in India. If you look at such data, it will be not thousands, it will be lakhs, right? Be it admission in JEE, be it admission in NEET, be it admission to this or that. You can do how many male admissions applied, how many admitted, how many female applicants, how many applied, and see, there will be differences, and you say this is because of bias.
Excuse me, sir. Can I give the solutions very simple? This university didn't have any gender bias. It's just that men happen to take easier courses than women. Women take the hard courses and take easier courses, so men get admitted more.
Wait, please wait. So your answer, what you are explaining, is probably right. It is. You will see. It will come in the next slide. The point is that what I call pure data-driven inference goes on this line, that if you just like my one of the other example we discussed, this one also, unless you know more, that where were the male applying, where are the female applying, and this and that, you can't deduce. And this is what, because such allegations were made, the professors at Berkeley actually looked at the actual data, and here is the data which is there from Wikipedia. You can also see, and easier and so on is a different question, but there are differential number of people selected. So there, as you can see, in some ones 62% are total selected is 64%, and there are some where only 6% are selected. So there is a differential in how many students are getting admitted, and likewise there are differences in how what proportion men and what proportion female. And then here we can see that in 4 out of 6 departments, the percentage selection amongst female is actually larger. So sorry?
No, that was some inverted, and you can just ignore it.
So you can quickly count and see that there are 4 out of 6 departments, the percentage selection amongst female is larger. So if you have to just go by this kind of analysis, then you will say, if at all there is bias, it is in terms of women. That also will be incorrect analysis, but this was just done to question or to answer that just that data on the previous slide conveys that there is a bias. It is not. It is just that some departments the percentage selection is higher, some departments percentage selection is lower, etc., etc. One can go on and on in the analysis. We can say that how many applicants had a high their actual scores in whatever exam you take, and so on and so forth. One can, if at all one has to say gender bias in a course, we'll have to go into a lot of analysis. Just on the basis of such a numbers given, one can't really say that there is analysis. So all that I'm saying is that what I call this perils of pure data-driven inference or pure data-driven analysis. Okay, that just because 30 students, their math, physics, chemistry scores are identical, they have cheated. No, you can't conclude that. That is data-driven inference, pure data-driven inference. That can be a starting point to explore whether such a thing is true, not certainly a decision making, and likewise this one as well. So if 44-35 was 44 and 20, even then it is nothing inconclusive. We need to get deeper into it. Okay, but this data is shown from actual event. Okay, now let me come to my last example I want to talk. It is again about getting deeper into analyzing where the data is from, what the data is from. Okay, so We are moving to 1940s, the World War II years. Okay. So this was very early years in aircrafts. It was in war as well as otherwise. Okay.
I've heard of
1940.
this.
Sorry, I would request people to put your questions to me and not interrupt right now. Professor Karandikar, I think you went on mute. Maybe. Yeah.
So these were early years of aircraft, and therefore there was no anti-aircraft guns either. Anti-aircraft guns will come when aircraft becomes quite a few being used in the war, then somebody will develop the anti-aircraft guns. So there were no anti-aircraft guns. So in World War II, aircrafts were flying low and usual guns were actually used to fire at them. So the British aircraft from London, they were flying, and they were flying to Berlin. They were not flying to where there was war going on, but they were going to the capital of their opponent. And likewise, German aircrafts were going to London and bombing the city. So it was more psychological warfare than real warfare, but nonetheless, it was happening. And as they were flying, they were flying all very low. They could not fly very high. The people could watch the aircrafts going. They didn't have anti-aircraft guns, but they were just using the standard guns and shooting at them. Again, on this, a whole lot of material is available on internet now. You just search World War II, aircraft, etc., and a few other phrases which will come in. Okay. Now, some aircraft went down, never returned, and some returned. Okay. And the returning ones, some of them were showing, most of them had hits. It was rare aircraft which was not hit at all because the distance was quite a bit. So someone in the British Army was, our Air Force or whatever, was keeping track, analyzing the data. That is, they were recording what. So let's say you divide the aircraft in 20 parts and you record how many aircrafts had a hit in this part, how many had this part, etc. And based on that, they've made a prediction that, these parts are hit a lot more. So maybe next level of aircraft, we should put some more strength there. Okay, so that was an analysis made. And because US was with them in the war, this data and analysis was shared with US. US, they were already engaging mathematicians to vet all such discussions. And Professor Abraham Wald, he was a consultant to US Army, and he somehow got hold of, he was the one who was asked this question, is this thing right? He saw it very differently. And his model, it is my words, but detailed I have read on the internet and various reports. Okay. So bullets were fired randomly on the aircraft, randomly in the sense I use it. They had no information, so they just hold it and shoot. And they were not targeting any specific part of the aircraft. They were just generally shooting at the aircraft. And the effect of hits on a given area of the aircraft were independent of the effect of hits on any other. That means today, typically there are two engines. Even if the aircraft can come back by just one engine, there are two. So if one actually goes down, you won't be able to figure it out because the aircraft is still flying. But if both engines are hit, aircraft will come down. So this is what means that the hit on one area, depending on the hit on the other area, are not dependent. Okay. This is again a very technical thing in statistics, probability, and comes in useful. So these were valid assumptions at that time, not valid anymore. And as soon as these two assumptions are made, probabilistically you can come out, and if you think, you also can come out with the thing that it is not the areas which are showing lots of bullet hits in the aircraft which are returning. If there is an area where no returned aircraft is showing any hit, that should be the one where you should focus your attention, because that means as soon as something is hit there, the aircraft is going down. That was the conclusion by Abraham Wald, and then it was accepted by the army and so on and so forth. Okay. So based on assumptions about the domain from where the data is coming, he came up with a model, and what came out with the conclusion is completely opposite to what a very naive, pure data-driven approach was giving. Okay? And this is again an actual example, an event which happened in a thing like World War, and huge things were at risk, and you can read as much as you want when you do search on Abraham Wald World War II aircraft. Okay, so basically the point is that whole lot of meaningful things are available through analyzing data. To meaningfully do that, you need to have some understanding of the domain from where the data is coming, how the data has been generated, and have some at least brief understanding of probability and statistics models and principles, and then you can really do meaningful things. Absence of doing probabilistic and mathematical and statistics analysis, you can be led astray completely, and these examples generated the same. So let me stop. This is exactly 20 minutes from the time Vinay alerted me. So now questions I can answer.